Okay. Welcome everyone. Thank you for coming today to David Bates's talk. My name is Stefanos Geroulanos. I am the director of the Remark Institute, and I'm going to go ahead and just introduce David in a second after thanking Amy Nguyen, Samantha Paul, and Katie Ackerman for the work that they have done in setting up a whole day-long event. This is the second panel of 3 that we're doing, and we're trying out to see how to work with scholars during a whole day, how to think with them for a whole day, as opposed to for an event with a sort of compressed time frame that comes in the Q&A. And David has very, very kindly agreed to be, as I said earlier, our guinea pig for this model of functioning. David Bates is professor in the Department of Rhetoric at the University of California, Berkeley, and he's the author of 2 books, Enlightenment Aberrations, Error and Revolution in France, and States of War, Enlightenment, Origins of the Political. He's also the co-editor with Nima Basiri of Plasticity and Pathology on the Formation of the Neural Subject, and his talk today comes from his forthcoming book, which I've had the great luck to read, supposedly secretly from David. Well, it was secret from David. And then afterward it no longer was. Yes, exactly. After I returned my notes, that was no longer. So I'm really delighted that we have the chance to actually see this product of many, many years of research and thinking, and a project that really covers the entirety of modern thought. Well, as much to, let's say the breadth of modern thought. And so, this is our chance to do this. So what we're going to do is David is going to give his talk, and then we're going to, in the Q&A, if you are online, please drop a question in the chat, or raise a hand so that we can actually go ahead and turn to you. So yeah, and that's basically the format for now. So David, it's all yours.
Great. So it's a pleasure to be here as always at NYU, but I really like this day-long event idea. So we'll see how the afternoon one goes, but thanks for the invitation. So as Steph said, this is based on a manuscript, which he kindly didn't say is really quite long to read as well. So I'm not going to try and summarize the whole thing, but I did want to give an overview of some of the sort of signposts of the whole project. So it'll be an informal kind of presentation of some of the aspects of the book, but I hope that if anything sparks your interest, we can discuss it more as we did this morning. So I'll start with a statement here from 1956, which is that one of the challenges of thinking is really how can we think about the brain as a machine, or in what ways can we understand the brain through contemporary technology? And both Claude Shannon and Donald McKay, innovators in information theory and AI, said that we can usually, obviously, as we talked about this morning. So the basic idea here is that when we conceptualize the brain, how can we design a machine which will simulate it? We're restricted historically by the kinds of machines that we actually have some familiarity with. So obviously in the 1950s, the machine that is par excellence, the model for the brain would be the new digital computer, as you can see with these early examples of both military and commercial computers as understood as giant brains. And that will lead to, of course, the whole dominance of AI, the parallel between human intelligence and computer intelligence becoming virtually indistinguishable, or at least highly similar. So this is basically the foundation of artificial intelligence as a research discipline, is to describe natural intelligence so precisely that it can be instantiated in a machine. And this comes out of Turing's work, but just generally as a principle animates artificial intelligence really from the beginnings in the 1950s up until the present. And we can just see an example of this. What this means is a kind of translation of natural intelligence into computer language, a kind of interesting comparison of the different kinds of discourses that we might find. This is what human intelligence looks like when it's being simulated by a machine, here in Newell and Simon's Human Problem Solving from 1972. So today we still live in this era of not only conceptualizing the brain through technology, but also through the technology of digital computer, whether we're literally simulating the cortex through the digital, or whether we're imaging the brain through the digital, or even today, we have the computer itself becoming like a brain with the development of what are called neuromorphic, neurosynaptic chips that basically imitate the structure of the brain rather than the von Neumann architecture. Not only that, do we have the possibility of the brain becoming like a computer with sort of transhumanist fantasies of implants and so on. But today you could say that not only is artificial intelligence the model for natural intelligence, but particularly in the contemporary era, as AI has become dominated by machine learning, we can see that the brain will be conceptualized itself as a machine learning system. So in other words, the brain or the computer, it doesn't matter which this image really, which one it suggests, whether it's the natural or the artificial, is basically a deep learning, natural language processing predictive system. And this is a diagram that shows sort of the blurring. We have a diagram that can be both a diagram of the hierarchy of the brain as a kind of machine learning system, or an artificial neural network. And we're in the strange position today where the brain is being understood in terms of artificial neural networks that are developed in machine learning. So the natural brain is sort of imitating an artificial neural network. But the main point is that the brain is a kind of computer and the computer is a kind of brain in contemporary discourse. But of course, we can go back, as Shannon and McKay themselves indicate, go all the way back to Descartes and see a kind of different perspective on the relationship between the artificial and the natural. And what I really want to do here today is to kind of defamiliarize a little bit the history of this conjunction of the computer and the brain, or the machine and the brain even, by thinking a little bit more about automaticity and some of its problems as we think about this history, because the dominant metaphors and the dominant models today in cognitive science and neuroscience is exactly that the machine of the brain or the machine of the computer is an entirely automatic device. And we may not be so aware of that in the humanities, but in the cognitive sciences, automaticity really reigns as a model. So what did Descartes say? Well, Descartes was using different machines. This is the famous grotto in Saint-Germain-en-Laye that had these complex automata. And he was saying that these waterworks could be understood as a way of describing the body, where the animal spirits are like the water, the heart, this artificial memory device. So what was interesting in Descartes' physiology is to think of the machinery of the body, as well as what I would call the information system of the nervous system, as a kind of technical system. And that is early on in the 17th century. But the other thing that is predicated on this theory is predicated on, is also the openness and plasticity of the brain. So not only does Descartes think of the body and the nervous system as a kind of technical system, he also thinks of it as essentially open, and as he says here, soft and pliant or plastic. And the reason for that is because the theory has to sustain a kind of explanation of learning and of cultural difference. As Descartes says, he could imagine the same human being, the same mind, the same brain, I would argue, if it was brought up from infancy among Europeans, or whether it developed elsewhere, as for example, among the Chinese or the cannibals. In other words, a completely different cultural being could develop from exactly the same physiological body. So Descartes gets caught up in this kind of mirroring of the machine, the body, and plasticity, as you see from a famous quotation from the Meditations. He's looking out at the window and seeing human beings here crossing the square. I would normally say I see humans themselves, men themselves, yet do I see more than hats and coats which could conceal automatons. I judge that they are men, but his judgment, of course, is based on seeing something that's not actually there. So this is what I wanted to kind of set in play right from the 17th century, is the fact that the mind, the body, the nervous system, and the machine are already imbricated in ways that require both a kind of plasticity as well as a kind of technical mediation. So here's an example of an automaton from 1650. But the language comes up in early modern philosophy to a great degree. Not only Spinoza, who first coins the term spiritual automata, but as in Leibniz here, understanding the soul as a kind of machine, which is not mechanical, as we know from his critiques of mechanistic thinking, but as he says, it contains something of the beauty of mechanism. So a spiritual automaton is a kind of odd mechanism that relates to this equally odd technical system of the body and its nervous system and its sensory organs. So we can move to Pascal, who also thought of the automaton as essentially the dominant way of thinking about human behavior. The automaton essentially was the cultured, learned behavioral system that is organized by a society, whereas the mind is something that has at least some sort of autonomy. But as he said, for the most part, we're driven by our automatic behaviors. Custom provides the strongest and most firmly held proofs. It inclines the automaton, which drags the mind unconsciously with it. So again, we have this emphasis on the pliability or plasticity of custom, and the problem, let's say, of natural intelligence being what is the role of the mind within this automatic system. So it's not a reductive theory, whether it's Descartes or Pascal or Leibniz, and yet there's an imbrication, as I said, of the technical language, the biological language, and the language of what we might call reason. So when we get to the Enlightenment, it's the perfect space actually for this kind of thinking. And I won't go into great detail, we could talk more about it later. But just to give you an example, we have a very small example, but one that I think is kind of telling is Hume in his dialogue says just some small touches in Caligula's brain might have converted him into a completely different person. So it's that same emphasis on the instability, let's say, of a plastic brain to be formed in one way or another, depending on cultural influences or physiological events, whatever they may be. And there's a whole way of rereading Hume through the theory of animal spirits and the physiology of the brain that I develop in the book that I won't go into here. So with Diderot, we have almost the perfect expression of this particular way of thinking, which is that memory, as well as learning, you might say, is dependent on what he calls the soft substance of the brain, as if it was a kind of living wax, susceptible to all sorts of forms, never losing any of those it has received, continuously receiving new ones that it retains. So this is a kind of open book that is written and rewritten and overwritten by data, you might say. But who is the reader? The reader is the book itself. So that the brain becomes a kind of self-organizing system, an enclosed autonomous system that is both imprinted from outside because of its plasticity, but also can be active in its own reading and rereading of itself. So this comes to the fore in a slightly cruder version, but an interesting one in Hartley's Observations on Man from 1749. He basically said that there were two automaticities that drove human behavior. The first one being the automatic, or what we might call autonomic physiological organization of the body. And what he called, this is a quote, the secondarily automatic function of cultural habit, which I would say in Hartley's work and others in the 18th century was explicitly understood as sort of the deformation, reformation, organization of the brain from the outside. So what Bonnet called a kind of second birth was the organization from outside of a pliant brain and nervous system. So alongside that imbrication of the biological, the plasticity of the brain and the technical systems, we have reason, which is sort of hovering outside, you might say. And one of the arguments you could make, or one of the narratives that we see in the history of thinking about artificial intelligence, is that reason itself begins to be understood in mechanistic terms. So this begins in this period of the 17th century with the first European calculators, which were designed not accidentally, we could say, by Pascal first in 1642. Here are some designs for his artificial reasoning device, which was a calculator. And then we also have Leibniz in 1671 designing a more successful calculator. I mean, more successful than Pascal's, but wasn't successful as an actual device. So this leads us to a certain kind of history then in artificial intelligence, which I want to critique, but I'll just give you the way that this kind of unfolds here, and then we can look at it more carefully. From the calculators, which continue to improve as we go through into the 19th century until we have very sophisticated calculators that are used in business and other domains. We have the automatic looms as well that are developed in this period. And the most important one that you probably are familiar with is the Jacquard loom, which has a kind of proto computer driven memory, which is stored on punch cards, which are very similar to early computer punch cards, where the pattern of the carpet is instantiated in a series of algorithmic steps that the loom automatically enacts. This is super important, not least in terms of the history of industrialization, but also as an inspiration for Charles Babbage. So in 1822, we now have what is the world's first automatic computer. The other ones, as you saw with the Pascal and Leibniz, you had to actually crank them yourself. This was an actually fully automatic computer system that was essentially a high-powered, high-speed computer calculator. But of course, with the inspiration of Jacquard's loom, Babbage developed what is considered to be the design for essentially a modern computer, a general purpose computer, which was one that ran more on functions rather than simply additions and subtractions as the calculator did. So as Ada Lovelace said, it wove algebraic patterns. That's what this particular machine could do. So it had essentially the same structure as a von Neumann machine, a central computer, a data structure, and data input. So over the course of the 19th century, we have development of a number of different machines that you might call automatic reasoning machines. William Jevons' logic piano, which is a great device, 1869, where logical syntax could be programmed in and then generate conclusions. And then remarkably, even in 1886, we have Charles Sanders Peirce developing the idea for logical gates as instantiated in electrical circuits. This is decades before Claude Shannon came up with the same idea in his work. And then we have Alan Marquand taking up Peirce's idea and sketching out a circuit diagram for what would be an electrical logic machine. So we're on the cusp here of something like a digital computer. So it's not surprising then, and this is what we could say would be part of a normal history, let's say, of artificial intelligence and natural intelligence. Someone like Peirce saying, look, whether we have a machine that is given premises that churns them in a certain way and then spits out conclusions, we can basically say the same thing is happening, whether it's a human, a man-machine being fed with these statements, or whether it's geared wheels in one of the logic pianos that's presented in the late 19th century. In other words, it doesn't matter whether it's an ill-understood arrangement of brain cells or the machinery of one of these logic pianos. That's basically the same. And this is where we get much more philosophical and much not only more sophisticated, but more radical theorizations that essentially a human being, like other animals, are just conscious automata. So even though we do have consciousness, everything is taking place within the brain, as Peirce said, sort of not very well understood, but it's just the churning of data and the production of certain kinds of responses. So in reaction to this, William James wrote about the brain. And this is where we can go back to even Descartes and say, one of the things that's missing here is what we already knew from the 18th century and before, which was that the brain is also what we might call open and plastic. So what James was trying to say is that in some ways, what's interesting about the brain are the least determinate, mostly vague and open parts of the nervous system. So the most perfect parts of the nervous system, in other words, the neocortex, where most of the complex thinking takes place, is actually the least organized or the most open and plastic. So plasticity, as he says explicitly here, and this goes back to other formulations like Diderot's, means the possession of a structure weak enough to yield to influence, but strong enough not to yield all at once. In other words, retaining form, but also capable of transformation. The other thing he mentioned about the plastic brain is that it's in an unstable equilibrium. So again, because it's the least determinate part of the brain, not the part that is the most organized by evolution, it's capable of doing unusual things. So this seems to put it at odds with the history of artificial intelligence, which is to emphasize the sort of mechanism of reason. What we have here with James responding to Huxley and others is the idea that the brain is a certain kind of machine, but it's a machine that has plasticity and openness and also this capacity for novelty. So we can see the 19th century brain is clearly also a brain that's highly determinate. The whole history of localization that takes place in this period is absolutely critical. So I don't want to diminish the importance of the work that was done to locate functions in different parts of the brain. But there's an equal and important history of brain plasticity that runs through the same discourse. And it reaches its culmination in the great British neurologist John Hewlings Jackson, where this is where James is getting his information from. If the highest centers of the brain were already organized, there could be no new organizations. So the fact of an idea of an intelligent being that is capable of novelty, is capable of new organization, the brain itself must then also be capable of developing a new organization. If everything was already organized, there would be no possibility of adjustments, as he says, in new circumstances. So it's important for a developing being, an evolving being, to have a kind of penumbra, let's say, or a shadow of plasticity in order for there to be evolution at all. And in the human, that space of plasticity was the neocortex. It was still undergoing evolution, and therefore was the place that had the most capacity for novelty and for new determination. So this is what both James and Peirce hit upon as a way of explaining what I would call genuine intelligence, which would be novelty and creativity rather than simply rote mechanistic deduction. James going so far as to say a brain with part of it scooped out, damaged, you might even say, is virtually a new machine. And Peirce willing to say, before Canguilhem even, that if a brain becomes diseased, it will begin to act in new ways, and disease may even cause an improvement in the general intelligence. So you can see how closely aligned here the idea of breakdown or failure can actually lead to a new organization and the complexity of thought that may be generated. So if James was willing to say that this was essentially something that was conditioned for all living beings, basically organic matter was itself plastic, then what we were forced to do is to say, where was plasticity most evident, or where was plasticity going to be capable of this potential for being read and reread and reorganized? Because plasticity was also a way of organizing the body in terms of habits, and habits are often difficult to break. But in the human, the brain maintained this sort of plasticity throughout its life, or at least part of the plasticity. So this history of plasticity goes right through the early 20th century and into the interwar period. I'll just give you one example here is Carl Lashley's important work on the rat brain. Basically, what he would do is train rats to run mazes and then cut parts of their brain out. And he realized that it didn't really matter what you cut out as long as there was enough matter left. It sort of reorganized around it, and they could still run the tests as before. So against localization, this idea that the whole brain could reorganize was important for thinking about, again, this capacity for new determination and what I would say for something like intelligent response. So this is just one example. There's many of them in the period of how thinking about intelligence uses the same sort of language as the brain sciences in the 19th and 20th century. So for example, this is a Swiss psychologist who was quite important in the day, saying that when we have novel situations, automatism doesn't work. So obviously in normal situations, automaticity is a perfectly good response because it's a learned response to a regular situation. But whenever we have a rupture, as he says, of equilibrium, when habit is not there to intervene, then we're disadapted. And intelligence is that particular act that takes on the task of readaptation. So we have this going on both on the side of the brain as a kind of unusual plastic machine. And we also have it in terms of psychology as a definition of intelligence itself. So clearly we can map the two onto one another. So what does that mean? Well, it seems to be a kind of break, let's say, in the history of artificial intelligence, because what we can say with some thinkers of the period is that machines don't have this capacity to change. As this commentator on Bergson said, a perfect machine, there's never any surprise. It just will always operate normally. None of the miracles, which are, so to speak, the signature of life. So we seem to have a kind of history here of plasticity linked to a history of vitalism, a kind of more metaphysical concept, let's say, of the living, as opposed to a history of artificial intelligence that emphasizes the mechanization of the body, mechanization of intelligence, and the mechanization of reason in actual machines like the logic pianos. So what to say about this? Well, along with Canguilhem, who also makes this distinction between the machine, which is not capable of improvisation, it's not capable of monstrosity, there is no machine pathology. We have to start thinking of an alternative. So even Peirce, who said we can't tell the difference between the man machine and the logic machine, actually said that's because the kind of deductions that were taking place were so mechanical as to not require any intelligence. So Peirce was much more interested in higher forms of thinking, like hypothesis and so on, that a machine was incapable of. It was destitute of originality, therefore could not reason like a human being, which required imagination. Well, I want to pay attention to something else then that lets us go sideways between these two histories, the one that would be like a history of the vital organism that cannot be reduced, and the other one would be a standard history of artificial intelligence. Because Peirce also says something quite interesting in some of his remarks on thinking, one of them being this: in my opinion, it is much more true that the thoughts of a living writer are in any printed copy of his book than they are in his brain. So there's something about Peirce that was willing to say, the brain is interesting, it's not reducible to a machine, but it's also not the case that thought is reducible to the brain, that thought has some sort of mobility, and it can lodge itself in like what we would call a form of artificial memory, like a book. Similarly, as he thought about brain disease leading to creativity and so on, he was saying, well, whether we take out part of the brain or whether you take away his pen and ink, the same problem occurs, is that thinking is arrested or interrupted. So if someone stole his inkstand, the very ideas would not come to me. So there's a sense that not only can we store thinking in artificial forms, but that artificial prostheses like writing are essential for thinking itself. So this is a development that I can trace in the interwar period, particularly through the thinker Alfred Lotka, who is a sort of biostatistician, but wrote this book on physical biology, which attempts to think about biology as in terms of the total biosphere. In other words, thinking of it as a physical system of entropy and anti-entropy, and trying to rethink evolutionary theory along that line. One of the things that he brings into his account is the utter radical exception of the human, because humans bring in technology to evolution in a way that no other animal does. So the era of man-made adjuncts to the natural body, these prosthetic organs, has given not only new direction to the process of evolution, but it's speeded up human evolution as well. And there's no parallel in the history of the globe. And that's because evolution of technology is unnatural. It can take place at a blinding speed, as we know today. So one of the things that he's interested in here is not only the technical condition of humans in their evolutionary context, but also that technology is in some ways a marker of what we call shared knowledge. In other words, that thinking in human beings takes place between individuals and through the medium of technology. And this is what he calls the thought transmitting propensity of the human species. So the brain now and the machine are not only the only two things in tension, we also now have to bring into a third element, which is what we today call extended mind or distributed cognition, the fact that thinking takes place between humans via technical prosthetics. So in the final essay that he wrote, one of the late essays he wrote at the end of the war, which saw the rapid acceleration of technical innovation to the point where we developed weapons that could literally destroy humankind, he talked about this as what he called exosomatic evolution, evolution that takes place outside the body. So what we call intelligence in particular is linked with this exosomatic evolution, not biological evolution, which is the evolution of technologies, artificial aids to what he calls our native receptor effector apparatus. Okay, so if we go sideways with Lotka, and here's a quote from Wittgenstein that echoes Peirce. I really do think with my pen because my head often knows nothing about what my hand is writing. From this kind of interesting quotation, we can go to Wittgenstein's more serious thinking on the matter, which was taken from these fragments written in the late 30s, early 40s, which I think gets at this problem that I'm interested in, is that nothing seems to him more natural than that there is no process in the brain correlated with associating or with thinking. It would be impossible to read off thought processes from brain processes. So he doesn't want to reduce thought to the brain. And this is not because of some inherent mysticism at all. I think it's much more to do with the collaborative or the social dimension of thinking, as well as the technical dimension. As he says, one of the most dangerous ideas for a philosopher is, oddly enough, that we think with our heads or in our heads. It's that idea that somehow thinking is in our head that is the occult or sort of mystical way of thinking about intelligence. What's much more realistic or more philosophically tractable is to think of thinking as a collective enterprise that takes place with prosthetic technical instruments. So as he says, is thinking a specific organic process of the mind, so to speak, as it were chewing and digesting in the mind? So chewing and digesting, those are things physiologically that could be reduced to a machine. There's a great art project, if you're interested, that is essentially an artificial digestion machine. But when you think about thinking, and this is in the 1930s, 1940s here, Wittgenstein's reflection here is really interesting. Can we replace thinking by an inorganic process that fulfills the same end? As it were, use a prosthetic apparatus for thinking. How could we imagine this thing, a prosthetic organ of thought? And that's something quite different than imagining the prosthetic reproduction or substitution of parts of the body, the physiological dimension of the body. So of course, we could imagine a prosthetic organ of thought somewhere around the same period in the 1940s if we were part of the secret projects both in America and the UK and in Germany to develop digital computers, because that's what we would normally think of as being the prosthetic organ of thought. And this is Alan Turing with the Manchester computer in 1949. So Wittgenstein read Turing's famous essay from 1950 on computing, machinery, and intelligence, which some people thought was just a joke. I mean, computing, machinery, and intelligence, just bringing them together was absurd. But as Wittgenstein said, I haven't read this yet, but I imagine it's no leg pull. So he was interested in this question, and you can see it reflected in Wittgenstein's own philosophical investigations on machines and thinking and so on. But what I'm interested in is actually Turing. So Turing would seem to be the one that was the most important for developing the digital computer. But what is this organic artificial prosthetic organ of thought? Well, the first thing is he said an automatic machine is something that is completely determined by its configuration. So none of the openness or plasticity that we associated with the brain in this other discourse that begins with Descartes. And this is essentially how the computer worked at the time. You had a complete determination of the system as an automatic machine. But Turing was reflecting on intelligence, and he realized that wasn't going to get at the essence of what we consider to be human intelligence. What he really wanted to be thinking about was transformation and learning and so on. So according to our convention, he says the machine is completely described by the relation between its possible configurations, and that abstraction cannot change in time. But what was interesting about the computer is that it was a machine that could be reconfigured. So as he said, it's possible to think about what he terms here the education of machinery. If we consider interference, we would say that each time interference occurs, the machine is probably changed. And in this sense, the interference modifies a machine. So the computer was understood to be open to determination. And by interference, we have to mean external interference. In other words, the machine is interfered with and therefore changes its configuration. Now, what's interesting is that Turing analogized this completely with human beings. What is a human being other than a machine that is subject to a lot of interference? In other words, learning, education, the programming of social, technical, political, mathematical, whatever kinds of forms of behavior that we want to explain, it happens because human beings are also open and subject to interference. At the end of a period of a large number of standard routines will have been superimposed on the original pattern of his brain. So the analogy between the brain and the computer is not reasoning machine and reasoning brain, but open plastic computer, open plastic brain, upon which routines are written and then rewritten and read, as Diderot said early in the 18th century. So there's Turing with his computer, the ACE machine that came out of the development of the military computer. But when he's working on this machine, and this is, I think, quite interesting, is that Turing says he's less interested in practical applications in computing than models of the action of the brain. So this is where his intellectual interest really was going to head. And the key for him, as it was going back to James even, or Hewlings-Jackson, was to see that the cortex of a human brain is what he calls an unorganized machine. So even though it was a machine, it was an unorganized one, and clearly the analogy was the computer was that it was also a machine capable of being organized. So the cortex of the infant is an unorganized machine, which could be organized by suitable interference training. And here is, I think, a super important point. A human cortex would be virtually useless if no attempt was made to organize it. So if, for example, we had like the 18th century wolf children raised without proper interference, they don't learn to speak, they don't learn to reason. I think that's what he had in mind. But if we think of the analogy with the computer, then we can say what's important about the computer is that it doesn't do anything until it's configured, until it's interfered with and therefore made to do something. So that was the plan, how to organize unorganized machines. And here Turing's playing around with early sort of neural network ideas to think about that. So when we get right down to it, then what was interesting for Turing was to say, of course, we need normativity, predictability, and even automaticity in intelligent machinery. But we also need what he called initiative. And initiative, I think, was related to plasticity, because as he says in this lecture, processes that are learned don't produce 100% certainty of result. If they did, they couldn't be unlearned. And what he wanted to do, as he said, was to discover this residue, the kind of in-between concept here of something that is left over, even though it's not a tangible thing. But I think what he's talking about here is plasticity. We want to try and discover this residue as it occurs in human beings and try and copy it in machines. So this is what I will do in the book, and I'll just point to it here just quickly, is that this is in fact something that was developed within cybernetics, the idea of a plastic machine that was capable of organizing and reorganizing. So we have, for example, Gray Walter, who developed the tortoises that you may be familiar with. The power to learn implies the danger of breakdown. So there's always a dialectic between sort of learning something new and breaking what was before. We have Ross Ashby, who developed the homeostat machine, saying every machine breaking down automatically readjusts its own internal organization until adaptation is achieved. So aligning breaking down with what we call a sort of reorganization. And just as James and Peirce said that disease could lead to new ideas, breakdown, according to Ashby, gives the machine fresh chances of moving to new equilibriums. In other words, kind of new opportunities for organization. Okay, so where are we? Right now, then we're at this point where we have the brain, we have the machine of the computer, and we also have the development of what we call exosomatic evolution, as we see here with J.Z. Young, who's a neurologist that was friends with Turing. One of the most important parts of the human evolution is the formation of artifacts, which is what defines us as humans. So instead of thinking about artificial intelligence as the history of the parallel or reduction of the human intelligence to the machine intelligence, I think we can rethink this as a triad of the brain, the machine, and what we call this technical condition, the prosthetic dimension. How do we use these prosthetic organs of thought? So this leads us to Leroy-Gourhan, who essentially was rethinking the origins of the human as a technical event. And it's not simply that we use technologies, but what was important for him was that technology allowed us to exteriorize the internal experiences of thought into concrete objects in the outside world, which was something that no other animal could possibly do. And this was linked with a kind of foundational plasticity. The most important fact, he says, is that the human brain has evolved in such a way that it remains capable of thinking everything, and that it is virtually empty at birth, which is what Turing was also alluding to. So human beings are defined by technology because they exteriorize thinking into artificial objects, which is another way of saying we can share thought, which is another way of saying you could never read thought simply off the brain. We had to look at the whole system in order to understand how, say, an intelligent operation is being produced. So as he says, evolution has entered on a new stage, which is the exteriorization of the brain, which is happening with the computer. And from a strict technological point of view, the mutation has already been achieved. So the real question of the time was then the computer, not necessarily now as an exact analog of the human, but more as what was its prosthetic capacity or its function within a technical system. So Karl Popper was reflecting on this in his work in the 1960s and 70s, and using Lotke's term, said human evolution proceeds by developing new organs outside our bodies. These are tools, weapons, machines, and so on. But for him, if we were thinking about cognition, the exosomatic evolution that was most important would be these, let's call them artificial memory and artificial prosthetics for the construction and creation of intelligence itself. So not only paper and pens, but printing presses, libraries, the whole collective, let's say, technology of human rationality and intelligence. And the latest one, which was the most important because it gave a sort of new conceptual apparatus for our thinking, was the growth of computers. So we have a very positive view of this in this period. We have Gregory Bateson reminding us that what thinks is not the human being or the computer, but it's the system as a whole. We have to think of this systematically. We have the innovators in human-computer interaction, like Licklider's man-computer symbiosis, saying the resulting partnership will think as no human brain has ever thought, and vice versa. The computer will be able to think with a human in a wholly new way. And that's essentially what is happening as we move into the 1960s, is new ways of thinking about how humans interact with their computers to produce new kinds of intelligence. So Douglas Engelbart would be one of the crucial figures here. And in the 1960s, he developed a whole theory which predates Latour and predates Edward Hutchins on distributed cognition, but where his whole point was that a human isn't just a singular thing with a kind of generating interiority and thoughts and then happens to express them later, but is actually this part of a functioning apparatus that includes language, technical artifacts, and methods, habits, in which this person is trained. So the human being is a kind of object that has been interfered with, who also works with interfering devices like computers in order to produce certain kinds of knowledge. And we can see that it's, even though it's highly technologized as an image, it does include a human brain that is capable of this sort of openness to its technical milieu. And precisely what Engelbart wanted to take advantage of here was the capacity of this system to respond to novelty and to adapt to rupture. So as he said, when the course of action must respond to new comprehension, new insights, and new intuitive flashes of possible explanations or solutions, it won't be orderly and it won't be predictable, but this is what the new automated HLAMT systems of tomorrow will give us the power. So even though they're automated, the fact that the human is working with these automated systems means that we have a kind of open and potentially intelligent system of both computers and human minds. So it seems reasonable, as he says, to say that this is the next level of our evolution if we think of Lotka's exosomatic evolution as what constitutes the human. So I'll just say that this idea of a distributed intelligence based on artifactual exteriorization even makes its way into the origins of what is now contemporary machine learning. This is the famous collection of essays called Parallel Distributed Processing, which reinvigorated neural network theory and lays the foundation for much of contemporary machine learning. This is a model of an entity, whether it's a natural entity or a computer entity, dealing with the world through neural networks. But what they said about intelligence was partly a critique of neural network theory and saying one of the things that seems to be missing in their own work was the idea that the human mind is intelligent in part, or maybe mostly, because of its ability to create artifacts, which are symbolic exterior representations that we can manipulate in new ways to gain answers to difficult problems. We can manipulate the physical environment, create, imagine representations, and manipulate them as if they were external, but inside our own minds. So again, we have this sort of blurring of the boundary of the external and the interior, and that what gives us intelligence is the ability to interiorize external artifacts and to exteriorize as well inside our own minds to provide whole new possibilities of imagination. So even at the origins of modern artificial intelligence, it was recognized that this was an important key to human intelligence, the extension of the mind through prosthetics. So we can look again, this is a relatively positive story, and someone like Andy Clark, the philosopher, is working with new models of the brain that essentially depend on machine learning models for their orientation. But we can say the mind is plastic. It's this potent organ of unsupervised self-organization that allows us to build and rebuild social, linguistic, and technological worlds. This new form of thinking is called predictive processing or predictive coding, and it essentially models human intelligence by taking their concepts and their methods from artificial neural networks and machine learning. So the brain is a constantly active prediction machine, constantly correcting for its errors and so on, and it requires this fundamental plasticity for its continual reorganization. But I want to end with just a kind of critical point, which is the way that my own book sort of concludes, which is we look at Stigler, who is Bernard Stigler, the philosopher writing his early work in the 1990s, taking up from Leroy-Gourhan, he's saying, yes, the origin of the human is this origin of exteriorization. We can only function with tools. That's what makes a human, is that it depends on tools for survival. So we can only understand ourselves through the way that the nervous system developed alongside technology. So the brain didn't develop and invent technology, the brain and technology co-evolve, and a human being is defined by this fundamental prosthetic condition. So what he calls exteriorized memory is, exteriorized memory is technical memory or artificial memory, and he calls these tertiary retentions, taking up the language of Husserl. But the main idea there is to say we have natural memory in our brain, but we have artificial memory in exterior technical objects. But what he argues more strongly is that, in fact, our natural memory is no longer natural, but conditioned by exterior tertiary retention. And the simplest way to understand that is that we remember things in language, and language is this kind of exterior tool, prosthetic of memory rather than a natural technique. So the fact that exteriorization of the mind is the condition of the constitution of the mind means that there's no such thing as an interior before the exterior. With Stigler, the mind is something that is constituted by its exteriorization and concomitant interiorization. So to get back to some of the earlier ideas that I started with, we can see that thinking is shared not as something that we own and then give up to someone else, but that intelligence and thinking, if we're thinking about human cognition, takes place between individuals via the prosthetics of technology. So I will just end with what Stigler's critique would suggest for the contemporary era as a kind of counterpoint to Andy Clark. Normally, what Stigler is arguing is that the individual thoughts that we have, in other words, our own psychic kind of cognition, is always a kind of reanimation of the dead, inhuman thought that is a technical artifact. So when we read a book, for example, it's already a kind of dead thinking that we reanimate. And because we are individuals with our own psychic dynamics, that's always going to be what he calls an event, something that's unpredictable. When you read a book, it's always unpredictable what you will make of it compared to another reader or compared to what the author has intended. The problem is that we now live in an age of what he calls automatic society, in which calculation has prevailed over every other criteria of decision-making. Algorithmic and mechanical becoming is concretized as logical automation and automatism. This is the development of what he calls a digital culture. Automatic society emphasizes this mechanical becoming through the logic of artificial intelligence. So all I would want to suggest, as we discussed a bit this morning, is that if we want to get back to the idea of intelligence as the decisive possibility of a new anticipation, a new organization, a novel solution to a difficult problem, then we have to emphasize not mechanical reproduction and automaticity, but this idea of decision as a cut or an intervention, a separation that allows something new to appear. And that's entirely at odds with what we would call prediction, which is literally to make known beforehand. In other words, to know the future before it takes place. What we really want to do is open ourselves up to a future that hasn't yet taken place. So unfortunately, in the digital economy, we're constantly being not just tracked, but captured by certain technologies that emphasize predictability. So that's one of the things that Stigler spent most of his time in the 2000s trying to critique philosophically. So the danger of the digital, according to Stigler, would be a short-circuiting of the individual as an event through this direct manipulation of the nervous system. We're no longer really reading a book as an event, but we're being fed certain kinds of things that speak to what we already know or what we already want. And that's something that's quite different. The other problem, which we can't get into in any detail here, is to say that what used to be discretely different forms of artificial memory are now being integrated via the digital infrastructure, so that we have more and more homogeneity in the cultural organization of memory, which is also leading to a certain kind of necessary predictability because of its homogenization. So if we want to then make a quick reference to Deleuze's postscript on control societies, which we have to do, I think, in the 21st century now, what counts is not the barrier, but the computer that tracks every person's position and affects a universal modulation. What Stigler says is we're living now in a hyper-control society because everything we do leaves traces. It's not even being whether you can enter into a certain building or enter a certain computer system. Our whole way of life is constantly being tracked by the generation of traces and the algorithmic predictability of those traces. So I just want to end then with what I consider to be the conclusion of my whole trajectory of this artificial history of natural intelligence, is to say that intelligence can't be prediction. It has to be based on concepts such as wandering, that's Heidegger, error, bifurcation, that's Stigler, or the essential category of the unpredictable. And that's where we have to go back to the brain. And even though Stigler didn't develop this in his own thought, he did recognize that the brain, like we've seen from Descartes and Diderot on, is an automatic machine. It's capable of automatization, but it is also plastic and therefore capable of disautomatizing its own function. So that's what we want to think of then as thought or intelligence, the power to disrupt and to disautomatize, that is, to change the rules. Thank you.